Hello, welcome to your AP Stats lesson on regression wisdom. I'm here with my trusty dogs, Daisy and Scout, by my side, and we are ready to talk about regression and residuals and how all kinds of different plots will help us know if our model is a good model. Okay, so we want to make sure the pattern is really straight enough. Why? Because linear regression only works for linear models, okay? Makes sense. A curved relationship between variables might not be apparent when you look at the scatter plot alone. It might be really subtle there, but it's going to be more important, more obvious in the plot of the residuals. Remember, you want to see just a cloud. You don't want to see any pattern at all in the residuals. The residuals are the leftover error, and we want that to be randomized. We do not want there to be a pattern to it. Okay, so if you look here, we've got we have data about penguins, which is just amazing. So here we've got the duration of their dives in minutes, and we have the dive heart rate over here on the vertical. And, a linear function might be a good model here. This is definitely a negative association, but you might pick up on the fact that there seems to be a subtle curve here. Well, you might pick up on that, but you might not until you look at the residuals. So if we look at the residuals, residuals can be plotted against either the x values, the y values, or predicted y values. Any of those are fine. Here we've got it against the x values. And you can really see the curve more pronounced in these residuals. And so what that means is we might want to consider other models that would be more appropriate for these data. So you always want to analyze your residuals. You're just not going to have a complete regression analysis without at least one display of the residuals. Usually we have at least two, something like a histogram and then a scatter plot, which we call a residual plot. They often reveal subtleties like we just saw, and we're going to need additional details when we find those subtleties, and that will help confirm or refine our understanding, perhaps look at a different model. Sometimes they reveal violations of the regression conditions that require our attention. All right, so we want to look at a histogram, dot plot, stem plot, normal probability plot, maybe. I think in this case, looking at the dot plot, histogram, or stem and leaf plot are more beneficial because you can find the modes, and that's going to be of interest to us. And then you want to look at your residuals. You can look at residuals, like I said before, against predicted values, against the x values from the data, against the y values from the data. Any one of them is going to give you a good visual to consider. Now, if we just considered the residual plot alone, then we might think, oh, yeah, model's great. We've got nice even scatter. But you'll notice we have a group up here that is a different color and a group down here that's a different color. Those come from the two modes that are to the side. Here we've got our big mode, and then here's our small modes. Modes away from the central mode, additional modes, are at times an indication of a different group or groups. So we're looking at predicting calories from sugar content in cereals. And so what we're seeing here is there may be three subgroups of cereals. A small one, a rather large subgroup, and another small one. So we found that there are these groups. We may decide that we need to analyze the group separately. We might discover that we want to report both the aggregated model and the disaggregated data model. Here's the thing, though, is for a model to be really a good model, all the data must come from the same group. So philosophically, at some point, a content expert is going to have to make a decision of whether these should be considered all part of the same group, or that we have three distinct groups. All right, so if we look here at the figure we have, the different groups they discovered were found on different shelves of the supermarket. So, group one is on the top shelf, group two is in the middle shelf, and group three is in the bottom shelf. Group three has the highest slope, which means that for calorie content, as sugar has a much larger impact um, on calories. For every increase in sugar, there's a bigger increase in calories. So it's probably really sugary cereals that don't have a lot of protein. Let's think about why those might be on the third shelf. If we're counting from the top, third shelf puts at eye level for children. Those are probably children's cereals. Two are probably just kind of your standard breakfast cereals. And then three are probably your high protein, low sugar, super healthy cereals. So in this case, if I were looking at the health of different cereals, depending on, if I were part of a consumer advocacy group or something along those lines, I would probably want to consider these as three distinct groups. Okay, so linear models give a predicted value for each case in the data. We cannot assume that a linear relationship in the data exists beyond the range of the original data. The further the new x value is from the mean in x, the less trust we should place in the predicted value. Once we venture into new x territory, such a prediction is called extrapolation. Extrapolations are dubious because they require the additional and very questionable assumption that nothing about the relationship between x and y changes even at extreme values of x. The extrapolations can get you into deep trouble. You're just better off not making them. Here's a time plot of the Energy Information Administration predictions and actual prices of oil barrel prices. And we want to know how the forecasters did. So here we've got the models down here, and then here we have the actual data. So something happened in the early 2000s, causing a sharp uptick in the price of oil. And whatever condition that was not accounted for in the original models. Extrapolation is always dangerous, but when the x variable is time, it becomes essentially an attempt to peer into the future. But you know what? Knowing extrapolation doesn't stop people. The temptation to see into the future is hard to resist. People want to make plans for the future, and these models are the best models we have. But you've got to give yourself a big margin of error. If you are in a position where you have to extrapolate into the future, at least don't believe that your prediction is going to be terribly accurate. It's maybe the best information you have, and you may be making the best prediction you can, but just know that it's pretty dicey. All right, let's talk about special points. We have outliers, leverage, and influence. Outlying points can strongly influence a regression. Even a single point far from the body of the data can dominate the analysis. Any point that stands away from the others deserves your special attention. So here we've got a scatter plot showing that something was weird going on in Palm Beach County, Florida during the 2000 presidential election. Here are the data for all the other counties, and you can see the relationship between the number of people who voted for Nader versus the number of votes for Buchanan. And you see here in this one observation for Palm Beach County, there is many, many more votes for Buchanan than would be predicted given the number of votes for Nader. Okay, so the blue line is the regression line once the weird point is removed. And then the red line is the one that includes the point for Palm Beach County. You can see that it has a considerable influence on the slope of the line. The linear model does not fit points with large residuals very well. Well, that makes sense because their predicted value is very far then from their actual value. Points with extremely large residuals are outliers. Because they seem to be different from the other cases, it's important to pay special attention to the points with large residuals. Another way, so a large residual, by definition of residual, the difference between the observed y and the predicted y, are going to happen vertically. But what about horizontally? It can also be unusual if its x value is far from the mean of the x values. Such points are said to have high leverage. A point with high leverage has the potential to change the regression line in a much more significant way, even than a vertical outlier. We say that a point is influential if omitting it from the analysis gives a very different model. Okay, so here we've got shoe sizes and IQs. And we are going to look and see the effect. Just notice that if we didn't have this extra point, it's just a very much of a cloud of data, which is great for a residual plot if we're looking for linearity. But in a scatter plot means there's no discernible relationship between shoe size and IQ, which makes sense. But let's say that there is a clown that actually that and we're looking at the shoe size of the clown feet. And let's say we have a genius clown. Well, in that case, it's going to pull a model up to it and it's going to inflate the value for R and make us think that a linear model is more appropriate than it really is. However, if we looked at a clown with an IQ at the other end of the spectrum, we would see that it's going to pull the slope of the line down toward it. It's going to increase the magnitude of the slope, but in a negative direction. This point would be influential. When you investigate an unusual point, you often learn more about the situation than we could have learned from the model alone. You can't just simply delete unusual points from the data. You can, however, fit the model with and without these points as long as you examine and discuss the two regression models to understand how they differ. Make sure that you look at the original scatter plot to look for influential points because they can often hide in plots of residuals. Remember, their extreme nature is at least in combination with being a far x value from the mean. Our residual outliers, our outliers in the direction of y, are going to show up in the residual plots. But these influential points often pull the line toward themselves, and so they actually sometimes have small residuals. You're going to see residual influential points much more easily in scatter plots of the original data. Or you can always find the regression model with and without the points, and if it changes significantly, then you know that point was an influential point. Okay, again, no matter how strong R squared is, how big big the magnitude of R is, no matter how well the points line up, there is no way to conclude from regression alone that one variable causes the other. There's always the potential that there's a third variable out there driving the values of both the variables you've observed. So let's consider some information about life expectancies and signs of other social conditions in countries. So here we have a bunch of observations for different countries, and it is relating the number of doctors per person. Actually, it's the square root of doctors per person to life expectancy. And you can see that there is a positive association there. But we cannot say, oh, let's just send a bunch more, many more doctors there in order to increase life expectancy. That would be tempting. Okay, there are people out there that would want to say that to promote life expectancy. But look at what happens here. if we compare the same life expectancy with this square root of TVs per person, we get an even stronger, it appears, um, linear relationship, positive linear relationship. TVs are cheaper than doctors, so maybe we should just send a bunch of TVs over to other countries. Well, that doesn't make sense. Well, here's what is probably actually the truth. Countries that have um, higher standards of living have more doctors per person and more televisions per person, and they also have a higher life expectancies for myriad reasons. So if the higher living standards actually cause all the other variables, cause the changes in them, cause the increase in them, um, improving living standards might be expected to prolong lives and increase the number of doctors and TVs. It's going to have the effect on all three. Again, the only way we can actually prove a causal relationship in AP statistics is to perform a well designed experiment, which would be hard to do with countries. Okay. Um, One of the things that people are tempted to do many times is to look at any data and apply what they learned from the data and the summary statistics of the data to individuals. The problem is there's more variability among individuals than there are among say, means of groups of individuals. Means are more stable. That's why on your report card, we don't just put all the grades listed on there. We don't pick one at random and let that be representative. We average them all together because your average is more stable than individual performance on any one task. So here we see that we've got a strong positive linear association between weight in pounds and height in inches for individual men. So here we go. Um, there's a good overall positive linear trend. There's one possible outlier. Let's look at what happens when you do the mean weight for each height value. So if we do that, then so you take all the men who are 64 inches tall, you average all those weights together, and then that gives you your data value. Okay, so this guy over here who's about 71 inches tall, who weighs more than expected, he's going to have maybe a little influence on the point in that general area, but not as much as before. So by averaging the weights together, we are decreasing the variability. So, what that means is if you've got a model that's based on mean values, you need to realize that that model is accounting for less variability than you'll see in individuals. Um, because means vary less than individual values. Um, so it gives a false impression of how well a line summarizes the data if there's any ambiguity left where people might think it's for individuals. It needs to be clearly stated if you are using averages, mean values as your as your points in your linear model. There's no simple correction for this phenomenon. Once we have summary data, there's no simple way to get the original values back. All right, so go ahead and pause the video and grab your book. Read over problem 22 on page 218. It's about ages of couples. Go ahead and pause. I'll be right here when you're ready. Okay, so we have several questions we want to answer. So, what is the correlation between age difference and year? Well, it's asking for R. We know R squared. We also need to think about whether we want the positive square root or the negative square root. There does seem to be a negative association, so R is going to be negative square root of 0.751. And so that's going to be approximately negative 0.8666. We want to interpret the slope of the line. This is one of the things that you need to be able, in your sleep, you need to be able to interpret the slope of a regression line. On average, for every additional year that passes, so every additional single increase in the units of the X value, The predicted difference in average age, so predicted Y value, is decreasing, that gets the sign, by about 0.017 years. We throw in the on average and the about and the predicted so that we are clearly indicating that we are talking about what's happening in the predicted values, what's happening in the model. This about here in particular lets people know that you realize there's scatter. It's not going to be in data that's observed from here on out. It's not going to be exactly 0.017 years every single time. It's going to average out to be that. All right, we want to predict the average age difference in 2015. That means we just plug in 2015 for X and we get 1.68. So notice we have a hat on our Y that's incredibly important because that communicates that we know that this is a predicted value from our model and not an observed value. Okay, describe reasons why you might not place much faith in that prediction. Well, we're extrapolating, okay? Societal conditions could change and the trend could be different. All right, so check out problem 24. Why is R squared higher for the first model in problem 22? Well, the points that were omitted were points with high leverage. Since they followed the same linear trend as the rest of the data, R squared was strengthened by their presence and weakened by their removal. Is the linear model appropriate for the post-1975 data? Explain. Yes, the residual plot reveals no underlying pattern and its spread is fairly small and even. So, confirm with the straight enough condition and we are good to go. What does the slope say about marriage ages? Well, on average, for each additional year that passes, the predicted average age difference decreases by about 0.023 years. Explain why it's not reasonable to interpret the y-intercept. Well, the y-intercept is going to be where x equals 0, and the data began with x equal 1975. So it would be a huge extrapolation to try to make sense of the predicted y value associated with x equals 0. Okay, so read the problem on page 217, number 18. What concerns you about the graph, the statistical methodology, or the conclusions reached? The graph shows a positive trend among average data for many individuals. There is too much variation among individuals themselves to make predictions for individuals based on patterns established by averages. All right, we're doing lots of examples. Read problem 27. All right. By removing one of these points, we could make the association appear to be stronger. Which point? Okay, and then explain. Well, the point for hippos. And the reason is they don't follow the general trend. So it's going to make the association appear to be stronger. Would the slope of the line increase or decrease? Okay, well, in this case, it would increase. Should we just keep removing animals to increase the strength of the model? Explain. No, we have to have a good reason to remove a data point. If we remove elephants from the scatter plot, the slope of the regression line becomes 11.6 days per year. Do you think elephants were an influential point? Explain. Yes, removing the data point lowered the slope from 15.5 to 11.6 days per year. So since there's a big difference like that, that means that the elephants were influential. All right, guys, that's it. Please do your problems to try on your own, and I will see y'all in class. If you need me before then, you're always welcome to email me or swing by and see me in my room. I will talk to you soon.